Bismillahirrahmanirrahim, lecture number 5, efficiency, the heat rate, and cogeneration in vapor power cycle. Um, let's start with the efficiency and heat rate. Normally, in thermal analysis of the cycle of power plant, the efficiency of the power plant and the power output of the power plants are of the main importance. Um, Thermal efficiency is obviously the work ratio or the work done divided by the heat supplied to the cycle of the power plant. But normally, what we have computed in this course, the thermal efficiency of power plants are less than that one. It is because what we have analyzed when we were analyzing the power plant, the cycle, the Rankine cycle, if it was superheat cycle or reheat cycle, or whether it was with a feed water heater, uh, we did not take account of various auxiliaries and obviously the various irreversibilities associated with them. There was non-ideality of the turbines. There was inefficiency of the pumps. There was friction losses, heat losses, the throttling losses. So many things, what actually we did not took them into our account. There was difference between the full load and the partial load operation. So let's say, for example, a power plant is actually designed for example, 1,000 megawatt, and for a certain day of certain time of a day, we are running it on a half load, like for example, 500 megawatt. So whether the efficiency would be the same as it was in a full load or not. So yes, we did not. There would be actually a difference between the full load and partial load. Um, there is actually, we call it as the gross efficiency, and gross efficiency is the one which actually is calculated based on the gross work or power of the turbine generator. So when we are talking about the work output from the turbine generator, we are talking about the gross work of the cycle. Um, then after that, we tap some of the power out of it for using the pump, for the various auxiliaries, and obviously the fuel system, and many things which actually would be we need power for running the power plants. So when we tap that power out of it, um, the power which we call it, or the net power, sorry, the power which we call it would be net power work of the power plant. So that mean like it would come up the net efficiency, and that is calculated by the net work of the power plant, and obviously that mean like gross power minus the tap power. So this is what we call it as the gross efficiency and the net efficiency. uh, Normally, when the power plant designers do, like, or the power plant designer, they are mostly concerned with the economy of the power plant rather than the the the, the efficiency and the so on and so forth. Uh, that mean like they are more interested in the efficiency, but in terms of the capital, in terms of the fuel cost, and in terms of the operating cost actually. So the main parameter which actually reflect these things, the fuel economy, it's one of them is called as the heat rate. Heat rate is the amount of heat supplied, mostly in BTU, per kilowatt of power produced. So that means like the heat rate is inversely proportional to the efficiency. That enhance that lowering the heat rate would mean like the higher the efficiency. Um, in other words, what actually I mean to say, like, lowering the heat rate would mean like we are supplying less fuel to the power plants, and we are producing more power output of the or more power output from it. So the heat rate is obviously one of the prime importance, and that means like it come up as the net cycle heat rate, gross cycle heat rate, net station heat rate, and so on and so forth. You can like, imagine like what kind of a heat rate we will be talking about. Let's have an example, but obviously that example itself is not so important to the values are not so important, but in actual what you the theme is of this example is that's more important. So a coal power plant has a turbine generator rated at 1,000 megawatt gross. A plant required 9% of this power for internal operation. It uses 9,800 tons of coal per day. The coal has a heating value of 11,500 BTU per pound mass. The steam generator efficiency 86%. Calculate the gross station, the net station, and the net cycle heat rate. Uh, so one important thing, what actually I need to discuss in this example is like you can imagine like if we have got a thousand coal power plant, 1,000 megawatt coal power plants, so you can say like a bituminous coal which has got a heating value of calorific value of 11,500 BTU per pound mass, then the coal required for that power plant would be 9,800 tons of coal per day. And you can imagine like if we have got a subbituminous or we have got like night coal, which actually we have got in a ther coal powers or ther coal sorry in Sindh station. So we have got that lignite coal, which has got a heating value of half of this one. So that mean like if I've got if I have same power plant, if I'm installing in Thar Sindh, so I would be needing mostly 20,000 tons of coal per day, and that mean like I would be having so much of coal burning in that coal power plants, and so much of the carbon dioxide, and obviously ash handling, and so on and so forth. So you can imagine the hugeness and also the difficulties running that coal power plants for 1,000 megawatt power plants in Sindh. So moving to our own calculation, the rate of heat burn, rate of coal burn. So we have got 9,800 tons of coal. You have to convert that tons into pound mass, multiply with 1,000, divided by 24. So you are running it for the 24 hours. So that means like 24 hour in a day. So that come up as 816,667 pound mass per hour actually. So you are burning this much amount of coal. Um, that come again gross station heat rate. So the amount of coal burn multiplied by its heating value divided by the kilowatt produced. So that means like it's in a 1,000 megawatt. So 1,000 megawatt multiplied by 1,000 would be you would be converting into kilowatt. So when you are multiplying, that would come up as a BTU per kilowatt hour. So that means like gross station heat rate is 9,391.67 BTU per kilowatt hour is the heating value. The station net power output is actually when you are subtracting 9% from it, that means like the total 91% is would be the net power output of the station. So that is 9,910 megawatt. So that come up as a heating value of heat rate of a station as 910. You can just change that 910 and you will get the net station heat rate. The heat rated to heat added to the generator as the generator is working in efficiency of 86%. So you can say like multiply with the 8.0.86 and then steam cycle and so on so forth. So the corresponding thermal efficiency, you can find the corresponding thermal efficiency using the heat rate and obviously the heat rate sorry, the corresponding thermal efficiency you can find using this. um, Now moving to the next topic, cogeneration in a steam power plants or cogeneration in power plants. The cogeneration system, they are normally the integrated system that would simultaneously lead to valuable product, the electricity and steam for the or the hot water from a single fuels input. Uh, The cogeneration normally is what we call it as a cost effective, cost saving relative to producing power and steam in a separate system. Normally, what actually uh, happen like when you have got when there is a requirement of hot water and there is also a requirement of a power plant, so there is actually a system, and that system we call it as a cogeneration system. In that cogeneration system we produce both these hot water and power in a single system. um, Cogeneration system are widely deployed in industrial plant like refineries, where you are actually where you need steam for the for certain purposes. Uh, Paper mill, yes, in paper mill you need steam for the process. Food processing plant, other facility requiring process steam, hot water, and electricity, machining, lighting, other purposes. So cogeneration is much more important in those industries or in those area when both the hot water or steam requirement is there, and also the power generation or the electricity requirement is there. District heating is one of the example of it. If I would say like district heating and district cooling is also the cooling is also one of the example of cogeneration. So district heating, in district heating, what normally is it is a community based power plants. In a community based power plants, we provide steam and hot water for space heating, and or vice versa if you are using it for cooling as well, and other thermal need with electricity for domestic and commercial use. For example, like in a district heat power plant that is actually in Manhattan building, uh, we the cogeneration power plant is actually producing electricity as well, and also it is actually providing the heating to the building as well. There's another example, like for you, you might have visited the local hospital over here, which is the Khabar Teaching Hospital. It has got a boiler installed at the back of the building, so that boiler is providing steam to the system as well, or steam to different processes as well, and also for the power generation, and also for the cooling HVAC system as well. So this is what actually we call it as a cogeneration. So when we have got both power output from the system and also the steam or the hot water from the system. um, Cogeneration, yes, they can be based in a vapor power plant, gas power plants, internal combustion engine, the fuel cell, and so on and so forth. But in our lecture, we will be actually discussing the Rankine-based cogeneration processes. Um, the first example of the cogeneration system is back pressure plants. A back pressure district heating plants that is shown over in this figure. The plant resembles simple Rankine cycle. Obviously, it's just a simple Rankine cycle with a a heat exchanger, which is actually attached to it, and that is actually producing steam for the export to the nearby community or for the various use. What actually we have got in a normal Rankine cycle, um, the heat is rejected to the environment using a condenser. So over here, so what we can do normally, we can attach or we can design a heat exchanger in such a way that we have got a water or the condensate coming from another point. We can actually move that condensate or water into the condenser. Once it's actually move out of the condenser, it will be actually hot, and we can actually or hot or provided like at a different pressure. If we are or if we are putting it at a higher pressure, we can produce steam as well. So obviously, what we are saying over here is the condenser heat, which is actually normally we throw out, or the condenser which is actually taken out its heat of the from the cycle Rankine cycle. It is used to to heat up the water from in another system, and that heated water or that steam is actually used in a building for the district heating or in a process industry for certain processes. So as I said, like in this figure, I said like it depend on the exit pressure a condenser or exit pressure of the cycle, which determine like whether we would be having a hot water over here or whether we would be having a steam over here. So that's why it's called a back pressure power plants. For instance, like if a steam is saturated vapor at 100 degrees centigrade is needed by the community, so the cycle working fluid assumed to be demineralized, obviously water, must condense at a temperature greater than 100 degrees centigrade. So obviously, if we have got a temperature greater at 100 degrees centigrade over here, so that mean like we can produce a steam which would be actually at 100 degrees centigrade over here. So that also mean like when we are exiting in the condenser, so that mean like we will be exiting in the condenser at a high pressure. So yes, you can imagine like higher pressure in a condenser would also mean like we are losing some power. So obviously there it is actually a takeoff, or it's a little bit, I would say like inefficiency that you can bear, because like you need to have a steam or hot water out of the power plant as well. Then there is another example, we call it as an extraction power plant. So in extraction power plant, it is not actually the only the condenser, which actually, no, it is not the condenser from where you are taking the heat output, but it is actually a roughly an example of the regeneration, or if when we have bleeded out the steam. So this steam, as in a regeneration, when we were bleeding out the steam, this steam was directed to a heat exchanger, and that heat exchanger, that heat exchanger, we can actually put on the water or condensate, and that mean like this heated steam can actually make a steam over here, and that could be actually used for the various processes in the process industry. Normally, it is normally in our process industry. So you can imagine like when we are extracting heat at this point and not at the exit of the turbine. So that steam over here is at the higher pressure. So when this steam is at the higher pressure, so you can imagine like when you are passing it in a condenser, so this steam can be of a higher temperature and a higher pressure also, so that because it has got the higher energy. So yes, you are extracting the steam, and sorry, you are extracting a little bit amount of steam from here, and let's say it's why, as we have discussed in a regeneration. So and that why mean like we would be having less steam which would be passing from here, and obviously in a cycle we would be having less power. But that's what actually I said, like in a normal industry, in industries, there is actually requirement of a power as well, but there is also requirement of a steam. So this kind of a power plant is used for both steam generation and power generation. Now, for a certain day, like yes, if the steam requirement is greater, you can increase the amount of steam extracted from this point. Or if for a certain day, like for example, there's a holiday or something, if there is no steam requirement, so obviously you do not extract the steam from here, and this process will not be there. So that means like it will be a total the power plant will be used for total power generation rather than actually for the steam and power. Next is the organic Rankine cycle. Organic Rankine cycle is a quite new Rankine cycle, and obviously there is a quite advancement of, in other word, I would say like there is quite a high research going on in our organic Rankine cycle. Uh, Typically, what that mean like organic Rankine cycle should use the organic substance as a working fluid rather than the water, and that include pentane, mixture of hydrocarbon, refrigerants, ammonia, silicon oil, and so on and so forth. Um, and it is basically why we need organic material. The organic material basically have got a low boiling point, so that mean like they're it can boil at a low temperature. When it boil at a low temperature, it also mean like it can produce power from low temperature sources that include industrial waste heat, that include geothermal hot water, and so on and so forth. So, and even the solar collector as well. So that mean like organic materials are now one of the prime importance in the prime importance, or there is a research quite going on in a organic Rankine cycle, and that is because of its low boiling points, and that because of you can produce power from the power from the low temperature sources as well. And then normally in literature, the organic Rankine cycle are normally referred as ORC cycles, ORC. Um, then we can say like binary vapor cycle. Binary vapor cycle, as the name would suggest, like there would be there would be a couple two vapor power cycle. We called these two power cycle as the topping cycle and a bottoming cycle. There would be actually two cycle, that mean like one would be the high temperature cycle, and then one would be the low temperature cycle. So the high temperature cycle would be extracting heat, or they would be throwing heat at a higher temperature, and the lower temperature cycle would be actually working under the high temperature cycle. In other words, well, let me explain on a diagram over here. That would be much more easy to understand. For example, we have got the topping cycle, which mean like high temperature cycle over here. So if we have got a topping cycle over here, so in a topping cycle, we would be having a boiler, we would be having a turbine, we will be having a condenser, a pump, and that's what we have got normally in a Rankine cycle. Uh, but then obviously from 2 to 3, when we are throwing the heat out of the system, and that is in a condenser. So they then we can install another cycle, or we can have another cycle coupled to the topping cycle, and that mean like coupled with the condenser of the topping cycle. That mean like we can have a low temperature cycle. Now this condenser in a bottoming cycle. This is our bottoming cycle now. So condenser in a bottoming cycle would act as a boiler for the bottoming cycle. So whatever the heat is actually rejected from 2 to 3, that would be accepted from in a bottoming cycle from D to E then. So that mean like there will be water heated from D to E. Once we have got once we reach at E, we can use the same boiler for the bottoming cycle to reheat a little bit more, and then we can utilize that in the turbine, and then condenser, and obviously the pump. So you would imagine like this would not much amount of heat anyway, but that's what actually it is a little bit designed for, that the topping cycle has got more power to it, while the bottoming cycle is actually using the same amount of heat, sorry, the same heat which is actually thrown from the topping cycle. So it is not intended for so much power, but yes, it is actually, it can give you certain power output. um, Also, like in the previous example, we did say like we have got the ORCs. That mean like the organic Rankine cycle, and that organic Rankine cycle, you can utilize a low heat to produce power. So you can imagine like if our bottoming cycle is having a ORC in it, so that mean like we can have a more power output of it. So from the TS diagram, you can say like the heat which is ejected in a condenser from 2 to 3 is accepted in a boiler from D to E over here. So that means like 2 to 3 is rejected, and it is accepted from D to E. While from E to A over here, we can utilize the same boiler to reheat or superheat the working fluid. So this is a concept of a binary vapor cycle, when we have got a high temperature cycle as a topping cycle, and we have got a low temperature cycle as a bottoming cycle. Then moving to another thing, another cycle, and that we call it as a superheat pressure cycle. Um, we have also we have already discussed that that in our first class, like the where the Rankine cycle work between two pressures. One is the boiler pressure and one is the condenser pressure. So by reducing the condenser pressure, we can increase the thermal efficiency of the Rankine cycle. While by increasing the boiler pressure, we can increase the thermal efficiency of the Rankine cycle. And I've said like I also said like the how much increase it could be. That would be actually up to the critical point. That is the maximum can actually increase the pressure would be to the critical point of the boiler. And obviously after increasing that, we would be not having any advantage anyway. So we have got the material now. We have got the new material advancement now, which can sustain this much amount of pressure, which is actually a pressure of roughly around 330 megapascal, and also a temperature of 600 degrees centigrade. So we have got the new material which actually can sustain this amount of pressure and this amount of temperature. So now we can have a boiler, or we can have a Rankine cycle which actually work in a supercritical temperature and pressure. So by supercritical temperature and pressure, that would mean like we would be having a maximum thermal efficiency that could be possible in a Rankine cycle, and that would be in a supercritical Rankine cycle. Um, Compared to organic and steam-based Rankine cycle system, supercritical carbon dioxide is also material which actually have achieved higher efficiency over a wide range of temperature and heat sources with a compact component, and that result in a lower, um, smaller system footprint and lower capital and operating cost. I hope you understand this theoretical portion of the Rankine cycle. If you have got any question in it, you can simply post in your Google Classroom, and obviously I would be able to answer that one. Thank you very much. Have a nice day.